All right, well, welcome to Lecture 4 on divisibility and the Euclidean algorithm. So let's get started here. Suppose we have integers a and b, and suppose b is positive just for the sake of making the picture nice. Then we can picture a number line which has like a on it, right? And if you think about it, there's got to be some multiple of b, which is after a and which is before a, right? And these should be successive, right? So like q plus should be q minus plus 1, right? Intuitively, a has to fit somewhere between a, like multiple of b. So, and more than that, we can see that the distance between, a and these multiples has to be less than b, right? Because the distance from here to there, since these are successive values of q, the distance from here to here is b, right? So if the distance from here to here is b, then surely a isn't more than b units from either of the endpoints, all right? And so if we set r plus or minus equal to a minus q plus or minus b, you can see that a is going to be equal to q plus or minus b plus r plus or minus. And here the absolute value of this remainder term is going to be less than b. Now, for example, here's an example. We could take, I'll scoot it up here a bit, but we could take a be 50, right, and b be 11, and if you just think about it, you can see that 50 is between 44 and 55, right? So it's between 4 times b and 5 times b, and indeed that gives us a remainder, like the r plus being 50 minus 55, which is minus 5, and the r minus, which is 50 minus 44, which is 6, right? So 50 is 4 from 50, 50 is 5 from 55, and it's 6 from 44. That's obvious, right? And so in this setup here, well, first of all, obviously I've just used, how did I come up with these numbers? It's just because I know basic arithmetic, right? I didn't really use a calculator here, but I will soon show you a strategy using calculator, which will involve our use of the decimal expansion of numbers and such. We'll get to that in just a second here. So here it is. So if we want to think about it, suppose you didn't have the common sense to realize 50 is between 44 and 55, right? How would you do it with a calculator? Well, here's one way you could do it. You could calculate 50 divided by 11, and find out it has a decimal expansion 4.54545454 and so forth. And so if we round down, we get 4. If we round up, we get 5. And so here, this notation here, this funny looking L, or I don't know what that is, but so like kind of like a hockey stick. Anyway, this is a notation which is used for the ceiling function. And that's the floor function. So the ceiling is the least integer, which is just above your fraction. The floor function is the greatest integer, which is just below your fraction, like that, right? So anyway, it's easy enough to see that that's 4 and 5 here, and that's why we did 4 times 11 and 5 times 11 as our numbers, multiples of b, which were before and after our a, right? So here's an example where I couldn't just guess it. Here I really need to use a calculator, right? So if I have a is 53,672 and I've got b is 68, if I calculate a over b with my handy dandy calculator, I get 789.294176 blah blah blah. So the floor of that is 789. And if I take a minus 789b, in other words, 53,672 minus 789 times 68, well, guess what? I get 20, all right? And so what that shows me then is 53,672 is equal to 789 times 68 plus 20, all right? So this is part of what we mean by, well, this is an example of the division algorithm, all right? So the division algorithm says that you can always kind of do this. You can find a quotient, you can find a remainder, such that A is equal to B times the quotient plus the remainder, and the remainder has to be smaller than B in magnitude. Now, to avoid using a negative remainder, we can just use the floor function, right? So if we use the floor function, then we're always going to pick on the number line. We're always going to pick on the number line the thing that's to the left of A. So then to get back to A, we'll have to add something, right? If you always wanted to use a negative remainder, you could always use the ceiling function to define your quotient, all right? But it's traditionally done. Traditionally, people want the remainder to be positive, so they use this number over here, and so we get a positive remainder. But it is just an ad hoc choice in truth. Okay, so let's go on here. Let me state the division algorithm more systematically. Here it is. Come on, we'll get it eventually here. So here it is, the division algorithm. What does the division algorithm state? It states that if you have integers a and b, all right, and we're going to assume b is positive for convenience, then there exists a unique, this means there exists a unique pair of integers q and r, such that a is equal to qb plus r, with where we call q the quotient and r the remainder, and that remainder has to be between 0 and b, not included, all right? And I will admit that I should mention, this is kind of a funny name for something, division algorithm. This is an existence theorem. It doesn't really give you an algorithm at all, right? The algorithm, if anything, you could describe what I showed you on the last page. You know, take your calculator, calculate the fraction, you know, use the floor function to figure out the quotient, and then, you know, use a minus the quotient times b to get the remainder. That's an algorithm. This is not an algorithm. But anyway, hey, everybody calls it an algorithm, so we're going to do it too. We're going to do it too. So here we go, proof. So what we do is we look at the set of all numbers that are obtained from a minus a multiple of b, right, minus some n times b, intersect with the natural numbers. So this is, by necessity, a subset of the natural numbers, all right? And since it's a subset of the natural numbers, and it's easy enough to argue that it's non-empty, here I do that right here. This bit of argument here shows that if a is less than 0, it's got a number in it, and if a is greater than, if a is non-negative, it's got another number in it. So this paragraph here just shows that, hey, the set S is non-empty. And since it's non-empty, that means it has a least member, right, via the well-ordering principle. And so we call that least element R. We let R equals to a minus qb. We basically let q be the choice of n, which obtains this least member. And in so doing, we have a is equal to b qb plus r. And so then it remains to show that the remainder has the you know, the necessary bound on it. So we'll proceed by contradiction now. If r is greater than or equal to b, then if we look at a minus q plus 1b, well, that's r minus b, and that is less than r under this consideration, which then means that we've got a minus q plus 1b is in S, and that's a problem because that's going to give us what? An element of S which is smaller, right? Smaller than r. But that's impossible, right? Because r is the smallest member of S. So consequently, we learned that r greater than or equal to b is nonsense because it led to a contradiction. And so we conclude that 0 is less than or equal to r less than b, which is what we needed. It remains to prove uniqueness. So let's look at that. So uniqueness. Suppose that there were 2 quotients and 2 remainders, right? Suppose that, scooch up a bit here. So suppose that, let me try to level things out here. Suppose that q prime, r prime were integers, such that r and r prime are both, you know, remainders. They're between 0 included and b not included. And they both give you qb plus r is a and q prime b plus r prime is a, right? Then, since this is equal to that, we can solve and get r minus r prime is equal to q prime minus q times b. Now, if q minus q prime is equal to 0, then great, we've got r minus r prime is equal to 0. So therefore, q prime is equal to q and r prime is equal to r, which is what we'd like, right? So what's the other possibility, given this equation, right? Well, either, let me look at it this way. Either q prime minus q is 0 or it's not, right? So if it is 0, we get what we want. If it's not equal to 0, then what happens? If q minus q prime is not equal to 0, then r minus r prime is equal to this, right? And since q minus q prime is not equal to 0, that's a non-zero multiple of b, which of course is greater than b. And that's impossible, right? You can't have the distance between the remainders, r and r prime, be larger than b, because r and r prime, right, they're fitting in the interval. Let's see if we can make sure it's in sight here. So since r and r prime, they're both between 0 and b, right? They're somewhere in this 0 to b number line, line segment number line. You can't have the distance between r and r prime be larger than b. That's absurd. So the second possibility that q prime minus q is not equal to 0 cannot be allowed. And so we're forced to the first possibility, which of course gives uniqueness. And there you go. That proves the division algorithm. Okay, so again, not a very good algorithm, but a comforting existence theorem nonetheless. So moving on here. Corollary to the division algorithm. All right, so here's a corollary to the division algorithm, which means a result that's related, but slightly different. Typically easy to prove, given the theorem we just proved, right? That's how the corollary works. If a and b are integers and b is not equal to 0, then there exists a unique pair q and r integers, such that a is qb plus r with 0 less than r less than the absolute value of b. All right. So the distinction here is that b is possibly negative, right? So first of all, proof-wise, if b is positive, then the absolute value of b is just b, and this reduces to the thing we just proved, all right? So suppose b is less than 0. That's the interesting case. If b is less than 0, then minus b is greater than 0. So we can apply the division algorithm to find q prime and r prime such that a equals to minus b, q prime plus r prime, right? Where 0 is less than r prime is less than minus b, okay? That's, again, by the division algorithm. And, okay, but then that means that a is equal to bq plus r, where q is equal to minus q prime, and r is equal to r prime. And that has 0 less than r less than minus b. But remember, minus b is equal to the absolute value of b in the case that b is negative. So there you have it. That's the corollary. So here's an example, which is kind of a neat example. I took it from Jones and Jones. In fact, most of this is taken from Jones and Jones elementary number theory. I've tried to make these notes self-contained, right? So if you don't have a copy of Jones and Jones, you can still understand it. But, the more books you have, the better. But here we go. So this is example 1.2 in that book on page 3. But anyway, if n is equal to a squared for some integer a, then we say a is a square. Okay, great. So we can prove that squares either have remainder 0 or 1 after division by 4. Let's see how. Okay. Dividing a by 4 from the division algorithm gives us a is equal to 4q plus r, right? And the remainder has to be less than the dividing number in magnitude, right? So if we're dividing by 4, our remainder is either 0, 1, 2, or 3. And so we can look at n equals to a squared, right? If n is a square. And it has to have the form 16q squared plus 8qr plus r squared. And then we can just explicitly look at the different cases, right? We can explicitly look at the different cases there. And what we see is r equals to 0, r equals to 1, r equals to 2, r equals to 3. Plug it in to this expression over here and do a little bit of algebra. You either get 4 times a number plus 0, 4 times a number plus 1, 4 times a number plus 0, or 4 times a number plus 1. And here by number I mean integer, right? So that shows you that the remainder of division by 4 is either 0 or 1 or 0 or 1. And we can be sure of this, right, because of the uniqueness of the division algorithm. It allows me to unambiguously conclude the remainders of 0 and 1 from the above calculations. All right. So there you have it. If we divide a square by 4, the remainder is either 0 or 1. So that's kind of a neat and a little bit unexpected example here, I think, at this point in the conversation. I will point out, though, that the thinking in example 3 is later replaced by elegant arguments by congruence, mod 4, in future lectures. I'm trying to remember when do we get to that in this course. It's a little bit. It is a minute or two. Okay, well, I've lost my schedule, so it's sitting here somewhere. I just forgot where I put it. So let's see here. What's next? Divisibility. All right, so now we got the Euclidean algorithm. We got the division algorithm, I should say. The Euclidean algorithm, in contrast, is an honest-to-goodness algorithm, so there's that. But before we get to the Euclidean algorithm, we need to talk a little bit about divisibility. So what do we mean by divisibility and the divides by notation? Here's the definition. This is important, right? You need to make sure you understand this carefully. If a and b are integers, and there exists another integer q for which a is equal to qb, then we say b divides a, and we write b divides a. We write b vertical line a, okay? This is not b over a. B divides a. B over a is a fraction, which may or may not be relevant to the current conversation. All right, so b divides a. In this case, we also say that a is a multiple of b. And if there does not exist a q for which a is equal to qb, then we write b does not divide a. Okay? And there are many beautiful properties of divisibility, but before I get to that, let me mention one of the important things that we'll use a couple times in the next lecture or two is that if b divides a, then a over b is actually an integer. Right? So a over b is actually equal to that q we just talked about, which is an integer. Usually, when you just take two numbers and you divide them, you're not going to get an integer, right? You're going to get a fraction, which can't be reduced to an integer. I should also mention that b divides 0 for all b. So 0 is a multiple of any integer. So sometimes we have to rule that out for different statements we make. Watch out for that. So here's the properties of divisibility, right here. We've got, let's scooch it up here a bit. We've got, if a divides b and b divides c, then a divides c. An example of that. 3 divides 9, 9 divides 45, okay? And so then 3 divides 45, all right? So here my a is 3, my b is 9, and my c is 45. All right. 2. If a divides b and c divides d, then ac divides bd. All right. So for example, 7 divides 14, 4 divides 20. So I'm thinking of a is 7, b is 14, c is 4, d is 20. Then 28 divides 280. 28 would be my AC, and BD would be my 280. So that's kind of neat. 3, if m is not equal to 0, a divides b if and only if ma divides mb. This is sometimes useful. If d divides a and a is non-zero, then the absolute value of d is less than a. So the magnitude of a divisor is necessarily less than or equal to the number which it divides. Okay? Equality can come when d is equal to plus or minus a, right? Okay. 4, and an example of that, let's see here, 13 divides 169, since 169 is 13 times 13. Of course, that's greater than 13, thus illustrating that the divisor is smaller than the number. Great. I'm sure you could come up with a better example than that one. I'm not terribly proud of this example, but enough about that. 5, if c divides a sub j for j equals to 1, 2, and so forth, then all the way out to k, then we have that c divides any integer linear combination of those a sub i's. All right. 7 is just a special case of, 7 is just another version of 5 with j equals to k equals to 2. But it's special enough that I singled it out, right? If C divides A and C divides B, then C divides AU plus BV for all integers U and V. We use this a fair amount. 6, if A divides B and B divides A, that's true if and only if A is equal to plus or minus B. I once gave a number theory class where I asked the students to prove A equals to B, and I was very happy when they told me that they couldn't do it. They're like, we need the minus. I was like, good for you guys. All right, so here's a proof of one. I won't prove all of these because I'm saving them for homework and test questions, of which they're great candidates for both. So suppose A, B, C are integers, A divides B and B divides C. Then that means there exists J and K integers for which B is equal to AJ and C is equal to BK. In other words, B is a multiple of A and C is a multiple of B, right? Thus, C is equal to BK, but I can take that B, right? I can take this B right here, and I can trade it for this over here, B equals AJ, right? So that becomes AJ, and then I've got A times L, where L is equal to JK, right, which is an integer. So I've shown that C is a multiple of A, which is to say I've shown that A divides C. There it is. There's a proof of one, and the proof of the others are pretty similar. I will say the proof of 6 is a little bit different in the sense that it basically comes down to solving the equation a number squared, I think, equals to 1 in the integers, which you have to go like, oh, well, the only way to solve that is plus or minus 1. If I remember right, that's what that one comes down to, but I'm not absolutely sure because I haven't worked it in a bit. Anyway, I'm sure I've given you at least one of those for a homework problem, and the other ones are good practice problems. I'm sure Jones and Jones has the proof of at least another one of those in there, probably two. Okay, anyway, moving along here. So the greatest common divisor is an important idea, and of course common divisors are also of equal importance. Here's the definition. If D divides A and D divides B, then D is a common divisor of A and B. For A and B not both 0, we define the greatest common divisor of A and B to be this. Well, we're just going to use the letter D here. I'm not saying that the letter D is universally reserved for GCD, but oftentimes I use it for the GCD in this lecture and the next. And so what does it take to be the greatest common divisor? Number one, you have to be a common divisor of A and B. And number two, you have to have that if C is another common divisor, right? If C divides what? Oh, see, I was, look at that. Marker got carried away here. That's supposed to be an A, right? Sorry about that, guys. So if C divides A and C divides B, right, in other words, it's a common divisor, then it must be the case that C is less than or equal to D, right? No common divisor of A and B is bigger than D. If me using bigger here bothered you, you might be an English major. Sorry. Now notice that we need them not both 0 because if you have 0, well, anything's a divisor of 0, right? Because 0 is a multiple of any number. And so so there would be no greatest common divisor if we had both of them 0, you know? So on the other hand, if they're not both 0, then if D divides A and D divides B, we can ensure that the magnitude of D is less than the absolute value of A, and the magnitude of D is less than the absolute value of B. And so that puts a maximum that the modulus, the maximum, words, a maximum that the absolute value of D could take, namely the product of the absolute value of A and the absolute value of B. All right, so we can be sure that there exists a common divisor. All right. So here's an example. Here's how I might have done it when I was a little kid. Find the GCD of like minus 12 and 20. Well, first of all, no teacher would have put a minus 12 there because that's just nasty. But I look at the factors of 12. Look at the factors of 20, right? 1, 2, 3, 4. 1, 2, 3, 4, 6, 12. Factors of 20. 1, 2, 4, 5, 10, 20, right? And then I look at common factors. 1 is a common factor, 2 is a common factor, 4 is a common factor. What's the largest common factor? 4, right? So the GCD of minus 12 and 20 is 4. There you have it, right? Now that's great, but that's not going to be a very good method when the numbers are very big, is it? Because then you're going to have to find all the factors of a big number. And this approach is going to be problematic. So we're going to find a better approach, which is called the Euclidean algorithm, all right? And we're not really going to find it. We're going to steal it from mathematicians who came before us, and who ultimately it goes back to Euclid, right, of ancient Greece fame. So anyway, here we go. Here's a lemma. If A is equal to QB plus R, then the GCD of AB is equal to the GCD of BR. Aha, that's kind of neat. So we don't change the greatest common divisor upon division by B. That's interesting. So here's the proof. If D divides A and D divides B, right, then R equals to A minus QB implies D divides R. Now, how do I know that there exists an R? Oh, excuse me, that's given in the lemma. Duh. So how do I know what's presupposed in the lemma is presupposed in the lemma? I don't know, maybe I could read the lemma. Okay, anyway, sorry about that. So we have R as A minus QB. And so since A divides that, and since D divides A and D divides B, it follows that D divides this by property 7 from page 4. Property 7 was this one. C divides this, C divides that, then it divides any linear combination of it, so we're using 7 here. So, all right, great. So that means that if you have a divisor of A and B, it's also a divisor of R, right? And of course also a divisor of B. So that means any divisor of A and B is also a divisor of B and R. So they have the same greatest common divisor then, right? Okay. So there you have it. So here, then likewise, if D divides B and D divides R, then since we can solve A's QB plus R, that implies D divides A. So, yeah. So we have the divisors of these two pairs are the same. All right. Okay. So what's the Euclidean algorithm? Let's get to it. The Euclidean algorithm is this. So you start. I always take A to be the bigger number in magnitude, just to keep things, nice. If A is, so I apply the division algorithm, all right? A is equal to Q1B plus R1, all right? Then we move B down here and move R1 down there. We divide B by R1. So B divided by R1 gives me a Q2, a second quotient and a second remainder. And then I move the first remainder down here, and I then divide the first remainder by the second remainder, and that gives me a third quotient and a third remainder. Then I move the second remainder down here, and I move the third remainder down there, and I divide the second remainder by the third remainder. That gives me a fourth quotient and a fourth remainder. And I keep doing this, all right? At each step of this process, we have the same set of divisors of, A and B. So A and B, and then let's see here. So let's see. Let me just try to track here. So we have 0 less than R1 less than B. Then the second one we have 0 less than R1 less than R2. Excuse me, 0 less than R2 less than R1, and so forth. Right. So then you can put these together. You've got B as the largest, and then R1 is strictly less than B, which is strictly greater than R2, strictly greater than R3, and you see down the chain here, right? Now, if these are strictly decreasing, right, and B is a number, this has to stop somewhere, because you can't go past 0 because these are all positive remainders, okay? Because we're using the positive remainder division algorithm. And so eventually they have to reach 0. So there's going to be an nth term which has remainder 0, and so that's where it stops. That's where the algorithm stops. And so it turns out that we can argue that the greatest common divisor of a and b is the last non-zero remainder. And that is how the Euclidean algorithm can be used to calculate the greatest common divisor. Now, if that didn't make a lot of sense to you, that's okay. Let's see how it actually works on some numbers. Okay, so here, a relatively simple example to start with. We want to find the greatest common divisor of 12 and 20 by the Euclidean algorithm, okay? So 20 is equal to 12 times 1 plus 8. So there's my first division algorithm, right? My first division, if you will. But you're like, that's not a division. That's a funny way of writing division, isn't it? Yeah, I mean, fair enough, guys. So, I mean, the division that we think about as children is what? 20 over 12. Well, that's an improper fraction, isn't it? So that's equal to the quotient 1 plus what? How many? That's 12 twelfths, right? So we still got 8 twelfths left over. So that's how we write division in grade school, right? But the division algorithm says you multiply that by 12. So it's 20 is equal to, 12 plus 12 times 1 plus 8, which we typically write like this, so that it has the same format as the division algorithm. So, I mean, it is division, it's written in a kind of funny way from a, elementary school arithmetic perspective, yeah? But anyway, so then we bring the 8 is our first remainder, then we bring the first dividing number, the b, down here, and we divide 8 into it, right? And 8 divides into 12 one time, it leaves you a remainder of 4. And then you bring this 8 down here, and you divide 4 into it. Well, 8 is 4 times 2, so the remainder is 0. Oh, that's n. So n is equal to, that's the last non-zero remainder here is 4. And so the GCD is 4, as of course we calculated by explicit enumeration of factors and just looking for common factors by brute force, right? So is this a better way to calculate the GCD of 20 and 12? No, probably not. But this one, I think it will be. Calculate the greatest common divisor of 1960 and 247. All right. So 1960 is 247 times 7 plus 231. Let me just do a little confession there. How do you find that? If you're using a calculator directly, right? What I would do is I would do 1960 divided by 247, right? And what's that going to give me? It's going to give me a number, obviously, but what is it? What does it give me? So 1960 divided by 247, I get, oh, isn't that funny? 7.93, blah, 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 blah. Right? So that means I should look at I should take, 1960 minus 7 times 247, and that will tell me the remainder. So 1960 minus 7 times 247 is 231. Right? And so that is a explicit calculator-based way. If all you have to work with is look a scientific calculator or whatever, you can figure out quotients and remainders like that, right? There it is. 1960 is 247 times 7 plus 231. And then you do that again. But this time I bring the 247 down here, and I divide 231 into it. Okay, that obviously just goes in once, and we get a remainder of 16. And then we do, the 231 brings down here, the 16 comes down here. How many times can we divide 16 into 231? Well, 14 times apparently, and the remainder is 7. Okay? And then we bring this 16 down here, and we bring the 7 down there. We divide the last remainder into the next. So 16, how many times does 7 go into 16? It goes in twice. and it leaves a remainder of 2, right? Because 14 plus 2 is 16. And then we bring the 7 down here. We bring the remainder to be the next dividing number. 7 divides by 2 3 times, right? And then we have a remainder of 1. When you get to 1, that's it, right? The next remainder is going to be 0. And so the last non-zero remainder is the GCD. So the GCD of 1960 and 247 is 1. And by the way, that property of two numbers having a greatest common divisor being 1 is important. What that means is that these numbers are relatively prime, or as is often also said, aka coprime. Okay, so coprime and relatively prime are synonymous. All right, A and B are coprime here. And there's another thing that's interesting is anytime next lecture we're going to look at something called Bézout's theorem. And Bézout's theorem says that anytime you calculate the greatest common divisor, you can build the greatest common divisor from a linear combination, integer linear combination of the numbers A and B. So let's see how that works. So you can reverse the calculation, and so let's see here, I'll try to keep it in frame. Reverse the calculation, and I honestly, guys, this particular calculation is it gives me so many fits. You can see I've whited out and redone. So I start with the last. The last shall be first. 1 is equal to 7 minus 2 times 3, and then 7 is equal to 3 minus 16 minus 2 times 7, which is the next thing. And then rearranged it. And then I plug in for the 7, I plug in 231 minus 16 times 14, right? Then I clean it up. And then next I trade my 16 for a 247 minus 231, which is up here. Clean it up. And then I trade my 231 for a 1960 minus 7 times 247, right? Clean it up, and I get 1960 times 108 plus 247 times minus 857 is equal to 1. And so this illustrates what's called Bézout's theorem. Now, please don't try to understand what I just did carefully. I mean, you can if you want to, but there's a much better way to do this called the vector Euclidean algorithm, which we'll cover in the next lecture. And also, if you're allowed to use technology, right, let me show you another way. So this is my wife's tablet, which is nice because it's big. Let's do here. Bill Cook Math website. That should do it, as long as I've got internet here. Wi-Fi is off. Oh, well, that's fun. Turn on Wi-Fi. Yes, please. Cookie, what do you know? All right, great. Can we go back to my thing? Let's try that again. Bill Cook Math website. Ah, there we go. BillCookMath.com. This is my brother's website. He's a professor at Appalachian State. Now, if you go in here, oh look, he's got cute kids. What do you know? You go click on that, and then go to Sage. And I usually just hit all demos. Bill has built a bunch of really nice little web-based things you can play with. A lot of them for calculus. We don't care about all that. I mean, I'm not saying you can care if you want to. But down here he's got the Euclidean algorithm for integers. I'll just click on that. All right. And this does the Euclidean algorithm for specific numbers. So, like for example, we could try putting in our 1960. And now, I should say, I do expect you to be able to do the Euclidean algorithm by hand. I mean, with like a calculator on the test. So don't use this for everything. You can use this to check your work, but you don't want to use it for, all your work. Otherwise, I mean, you should use it to check your work, is what I'm trying to tell you. And it'll be very helpful to you as you're trying to learn it. Yeah, there it is, as you can see. Maybe you can see. some kind of resonance between my light bulbs and this thing, isn't there? Or the tablet. I don't know. It's funny, the sampling rate and the sampling rate of the camera, when there's some kind of resonance, you get these like banding lines and such, but whatever. Anyways, as you can see here, those are the calculations that I just went through, right? And I mean, this is such a wonderful tool to be able to check your answers like that. But anyway, I have a link to this website in the problem statement for your current homework set, if I recall correctly. It's like, well, you can't see it here, right? Because this is a, paper. But where it says click here, if you look at the PDF of it, there's actually a link to Bill's Sage interaction there. So, all right, well, that's it for this one. So, thanks, guys.